Okay, everyone, so we're looking at the pH scale review from what you've already learned in grade 10 and ways to calculate how do we determine the pH of a solution. Okay, so just to recap what we learned already so far, we know that acids ionize when they are in water and they produce hydrogen ions, correct? So here we have, let's say, gaseous HCl ionizing in water. We have hydrogen ions and chlorine ions, right? Really? So acids always will ionize to produce hydrogen ions, right? And bases dissociate to produce hydroxide ions. And of course, we know that molar concentration is always the amount of moles of a substance with the volume of a solution in liters. So the reason why we're going over molar concentration is because the pH scale is really on the basis of hydrogen ion concentration. Typically, the more ions that are in solution, the more acidic it is. And the pH is actually the opposite. It is lower on the pH scale, the more and more acidic a solution gets. We're going to review all that. So pH is a way of indicating the concentration of hydrogen ions in solution. Of course, we know hydrogen ions are the main reason why we have properties of acids as we do, whereas bases are hydroxides, right? Arrhenius, we've seen this name before. So Arrhenius is the person who first looked at dissociation and ions in solution and how they behave. So he contributed actually quite a bit in terms of our knowledge of acids. So here's just a very simple pH scale. So it runs from 0 to 14, 7 being in the middle, which is neutral. Anything lower than 7 is considered to be an acid. Anything higher than 7 is considered to be a base. So as mentioned before, the lower on the pH scale that we go here, the more acidic the solution is. Why? The concentration of hydrogen ions is increasing as you go to the left. As you go further and further to the right, you actually become more and more basic. And instead of hydrogen ions becoming higher, you have hydroxide ions. So when we're looking at this, obviously we're going to be looking at calculations involving hydrogen ions and how we can actually determine the pH. So as mentioned, it's going to sound like a broken record here. The higher the concentration of hydrogen ions, the more acidic a solution will be, the lower the pH number will go. The higher the concentration of hydroxide ions, the more basic a solution will be, the higher the pH number will go. So of course, we can classify an aqueous solution as being one of the three categories, acidic, neutral, or basic, based on the type of concentration it has for hydrogens. So here are some numbers. So when we have a neutral solution, the hydrogen ion concentration is 1 × 10⁻⁷ moles per liter. So obviously, as we mentioned, the higher the concentration of hydrogen ions, the more acidic. So if this is considered to be neutral, right? No, it's not an acid or a base. For it to be acidic, it would need a higher concentration than being neutral. And if it's basic, it should have a lower concentration than the neutral number. So here is our pH scale. So neutral is again at 7. So you have some examples of different substances here. So of course, the increasing acidity as we go lower and lower, if you look at the concentration, so these are concentration numbers at the bottom here. So here is the 1 × 10⁻⁷. As the concentration gets higher and higher, the pH goes lower and lower. And then the opposite is true for the base end of the scale. Now, there is actually a pOH scale, which is essentially the same thing, except instead of being a measurement of hydrogen ion concentration, it's looking at hydroxide ion concentration. So it's actually the opposite. So the 0 to 7 is a basic range, and 7 to 14 is acidic. So remember that when you have higher concentrations of hydroxide, the pH number becomes lower. So here you have lots of hydroxide ions, right? The more hydroxide ions you have, the more basic it is. Whereas on this side, when you're dealing with an acid, you don't really have hydroxide, you have hydrogens. So the concentration for hydroxide is very, very low. So you're going to see us look at this pOH scale again in a second. Okay, a lot of this is repetitive. So acidic solutions we know is anything below 7. The lower the pH, the more acidic, the higher the concentration of hydrogen ions. Basic solutions have a pH more than 7. The higher the pH, the more basic, the lower the concentration of hydrogen ions. And that should make sense because you have hydroxide instead. So when you have a pH of neutral, you have equal quantities of hydrogen and hydroxide. Because when you have hydrogen and hydroxide in equal amounts, well, you get water, which is neutral. So here we have this kind of an empty diagram here with a bunch of different terms. So pause the video and see if you can identify where things should be placed on this scale. All right, let's see how you did. Okay, so neutral should be at 7. Actually, to do this nicely, we should kind of do this. 7. Bases above 7, acids below 7. So low pH, right, means obviously you are lower on this scale. High pH should be somewhere over here. So strong bases. A strong base should have a high pH. Remember that the higher above 7 you go, the more and more hydroxide you have. So a weak base should be close to 7. Obviously, anything higher than 7 is considered to be basic. Pardon me. So you should have it definitely not near 13 and 14, but somewhere over here. Same thing with weak acids, but on the opposite side. So the lower the pH, the stronger the acid. So your weak acid is anything below 7. Obviously, I would say the weak range would be anything from 3 to 7, but the weaker it is, the closer to 7 it is. Same on this side. The weaker the base, the closer to 7 it would be. Okay, so let's take a look at calculating hydrogen ion concentrations or calculating pH values depending on what we're looking for. So we already know that we can have acid, base, or neutral. So let's look at our formula. So here you have pH is equal to the negative log of the hydrogen ion concentration. So everyone should be using a scientific calculator at this point in time. You have a button on there that has log. So that is a logarithmic scale. You're telling your calculator to calculate this in logarithmic scale values. You'll learn more about how that actually functions in math class. So we're not going to go into details. You just need to know for chemistry, where do you find the button? Okay, so let's just do a quick example to see if you know how to put this in. So let's say we had a concentration of, well, let's put this in our calculator. So you would put negative. Then you would do the log button. Okay, and let's do 3.1 times 10 to the negative 8. Okay, so in your calculator, make sure you're putting this in brackets. Bracket 3.1 times 10 to the negative 8, close your bracket. If you don't do that, you will only take the log of 3.1. You need this entire number. So let's see how you do. Times 10 to the negative 8. So we should get a pH value here of 7.5, 7.51, if you've done this correctly. Now, some calculators do this in the opposite way. I'm not sure why. So if your calculator if you did not get this answer when you put this in, first of all, make sure you have your brackets here. Okay, if you don't put your brackets, you're going to end up getting negative 0.58. And that's incorrect. So you're going to do negative log in brackets. If you don't have this, your calculator may want you to put the number first, still in brackets, then hit log, then hit negative. I'm not sure. Every calculator is a little bit different, so you'll have to try that out. So anyways, you should get 7.51 here. pH actually does not have any units. It's unitless. There's not too many of those out there. So this is an example of one. Now you can also solve for pOH. It's the exact same formula, except it's a hydroxide ion concentration. So obviously you have to be consistent. If it's pH, it's H. If it's pOH, it's OH. Now you do have a relationship between the two values. So once you know the pH or the pOH, you can always solve for the other thing. So for example, let's say I wanted to solve for the pOH up here. Okay, well, pOH would be 14 minus the pH. So because I have pH, I can solve for that. So 14 minus 7.51. Right, so the pOH would be 6.49. So once you have, this is a very useful relationship, because sometimes you might have only hydroxide, but the question's asking you for pH. You cannot solve for pH unless you have H. So the only way around that is to do it with this formula here. So here's a very simple introductory example, and we'll do some other ones in a second here. So what would the pH of a solution be if we have 1.0 times 10 to the negative 2 moles per liter of hydrogen ions? Right, so very straightforward. They're giving us the hydrogen ions, which is very nice. Right, so if we do this, negative log, remember your bracket, times 10 to the negative 2. So we should get a value here of 2. So pH of 2. So pOH, if you had to, would be 14 minus 2 would be 12. All right. Now you do follow sig figs here. So for 1.0 times 10 to the negative 2, we would have to add a 0 on, but there's no unit for pH. Now, this is obviously very straightforward. How can this get more complex? Well, maybe you're told the actual, the acid itself. So let's say we have a hydrochloric acid solution. It'd help if I spelled that right. I'm so used to doing short forms, it's like forget how to do the, we'll keep it consistent. We have a hydrochloric acid solution of 0.0025 moles per liter, and we want to know the pH. Okay, well, you have to remember that this is essentially ions in solution. So this is really hydrogen ions and chlorine ions. So when we talk about this concentration, it's a 1-to-1 ratio with the ions that are produced. So this actually is the hydrogen ion concentration. So the pH of this solution would be negative log of the concentration of our acid. All right, so negative log, and this is moles per liter, of 0.0025, right? So this would be a pH of 2.6. Now, what if you had something that wasn't a 1-to-1 ratio? So let's say we had 0.003 mole per liter of sulfuric acid. Okay, well, for every 1 sulfuric acid, there are 2 hydrogen ions that are produced. So really, if I want the concentration of hydrogen ions, it's going to be double the concentration of the acid. For every 1, there are 2 hydrogens produced. So when this becomes ions, I have 2 hydrogen ions and 1 sulfate ion that are made. So the concentration has to reflect that. Remember, we don't care about the concentration of the overall acid. We want the hydrogen ion concentration. So the pH here would be negative log of 0.006. Negative log of 0.006, which would be 2.2. Okay, so be careful, obviously, looking at your compound. So we'll look for, let's look at the next kind of level of difficulty in the next video part.